So in our last lecture, we talked about what are ordinary differential equations, different types of ordinary differential equations, and we have discussed why differential equations are so important in science and engineering, in modeling important physical phenomena. Now in this lecture, we'll talk about first order ordinary differential equation. In particular, we'll look into few analytical solution of first order ordinary differential equations. As this part of the course will go on, you will see that in many cases, especially in initial value problem, even the higher order ordinary differential equations are first transformed to a series of first order ODEs and then solved. So solution of first order ODE is particularly important in numerical methods. And the analytical solution is important because it gives us the idea quickly, the nature of the solution. Numerical methods are not easy to employ all the time. That is why knowing beforehand how the solution might be actually helps. And that is where analytical solution comes in rescue. A first order ODE is of the form dy dx is f of xy. They are always initial value problem, have one initial condition at x equal to x naught, value of y is y naught. This x in most cases you will find it as time. So in many cases first order differential equations are always written as dy dt. Because in most application this x means time. Now there are several first order ODEs that can be solved analytically. The list is very long and we are not going to talk about everything, but few examples I'll give, few types of ODEs, first order ODEs that can be solved analytically. We'll see that here. First type or simplest type of first order ODE that we can solve analytically are what we call separable ODE. In separable ODE, x and y, one can be taken on right hand side, another is left hand side. So for example, let us take this dy dx equals x plus 1 e to the power minus x y square. Clearly, here we can separate first. So I can take this y square toward left side and dx I can take it right side. So after separating, it becomes dy by y square equals x plus 1 e to the power minus x dx. Now we can integrate both sides. Once we integrate, we have minus 1 by y is equal to minus x plus 2 e to the power minus x plus c. C is the constant of integration. So we can write this y equals 1 by x plus 2 e to the power minus x minus c, and the c then can be found from appropriate initial condition. Let us take one more example. Here dy dx is y square minus x square divided by twice xy. Looks like that we cannot separate it, but we can play around and try to separate it in a slightly different way. Here we can write the right hand side as y by twice x minus x by twice y, and then this y by x I can write it as u, therefore x by y is 1 by u. So now the left hand side becomes u, and since u is y by x, I can differentiate both sides here, and what I get is dy dx is equal to u plus x du dx. So then I can replace this dy dx over here, and what I get is an differential equation of u and x. Now taking this u to other side and then separating it, I can see that now I have 2u du 1 plus u square minus dx by x, so it is separated. And we can continue with the integral. It gives us log of 1 plus u square is equal to minus log of x plus c then of course in place of u, I can write y by x. The second type of first order ODE which we can solve analytically are something we call exact ODEs. They are of the type of m dx plus n dy equals 0, where m and n are both functions of x and y. This equation is called exact when this m dx plus n dy is equal to du, where u is some function of x and y. In such cases, we understand that we can write du equals 0, that means u equals constant will be a solution of this equation. Now we have to identify that when this can happen. So if this happens when it is exact, if it is exact, then del u del x is equal to m and del u del y equals n. Why? Because this del u del x multiplied by dx plus del u del y multiplied by dy is equal to du. That means n is del u del y and m is del u del x. If this happens, then I can say that del m del y is equal to del 2u del x del y. Similarly, del n del x is same as del 2u del x del y, which means these two are equal, and we can test if they are. If they are indeed equal, then the equation is exact. Once we find that this is exact, then u equals c, that will be the solution of this, that can be obtained from this del u del x equals m or del u del y equals n. Integrating from here, we are not going back over the main equation once again. We can just try this. So u will be then m dx plus p of y, since this is partial. So p of y partial derivative with respect to x of p of y will be 0. And similarly from the other side, u is n dy integral plus q of x. Now let's see an example here. Let us say we have this equation cos x plus y dx plus 3y square plus 2y plus cos x plus y dy equals 0. So here I have this m is cos x plus y, and then n is 3y square plus 2y plus cos x plus y. Now is this equation exact? We have to test that from here, del m del y and del n del x. If I find this del m del y and del n del x, I see that both of them are minus sine x plus y. Here for n, when I am differentiating with respect to x, the partial derivative with respect to x, when I am calculating that, partial derivative of this part with respect to x will be 0, because y will be treated like a constant. So we see that del m del y equals del n del x, therefore this equation is exact. And now we can find out this u, which will be m dx plus py and n dy plus qx. If I integrate this m dx, my m is cos x plus y. If I integrate that, I'll get sine x plus y plus some function of y. My n is 3y square plus 2y cos x plus y. If I integrate that, I'll get y cube plus y square plus sine x plus y plus qx. So both are u, so these two should be same. Sine xy is already there. P of y, function of y, that is already there. Q of x, nothing is there, so q of x must be a constant or 0. Therefore the solution will be this sine x plus y cube plus y square is a constant. Now when I have this kind of equation but del m del y del n del x are not equal, then I can multiply a factor in this equation to make a new m and new n such that the exactness prevails, and that factor is called integrating factor. For example, this is an equation dy dx px plus y equal qx. The left hand side, if I can write the left hand side as ddx of some function, then I can easily solve this. But how do I write that? To do so, I multiply both sides by integrating factor rx. So it gives me r dy dx plus rp y is equal to rq. Now we expect that this left hand side, this r dy dx rx px y, this will be equal to ddx of ry, because if it's so the first term is satisfied, we can see that first term will be r dy dx. So if I differentiate ddx of ry, I get this r dy dx plus y dx. R dy dx is already there, so therefore this y dx and rp, they should match. When they match, then dx is equal to rp, or r is e to the power p dx, so that is the integrating factor. So in this case, the left hand side will be ddx of y r, and r is e to the power p dx, and I have multiplied r both sides, r is e to the power p dx into q. So now this equation is solvable. I can integrate both sides. Left side is y e to the power p dx, right side is e to the power p dx q dx integral plus constant. Now I can evaluate this integral on right side and apply the initial condition to get the c that will complete the solution. So let us take this equation dy dx plus y tan x is equal to sine 2x. Here initial condition is x equal to 0, y is 1. So here the integrating factor r will be e to the power tan x dx, and then from here I can write y is this e to the power tan x dx other side, so e to the power minus tan x dx within integral e to the power tan x dx sine 2x dx, and then there is a constant. I can write this as cos x, e to the power tan x dx will be cos x, and then on other side this is sec x sine 2x dx. For this tan x dx, you can see that tan x dx is, you can write is sine x by cos x dx, and then you can take this cos x as z and you can evaluate this integral. That is how we will get this cos x and sec x. E to the power minus integral tan x dx will be cos x, and e to the power plus integral tan x dx will be sec x. Then I have sec x to sine 2x. Sine 2x is 2 sine x cos x. So cos x into sec x 1. So only sine x will prevail here. So cos x 2 sine integral sine x dx. So that gives us c cos x minus 2 cos square x. Now you can apply the initial condition here and you get this c equals 3. Therefore, the solution of this equation comes out to be y equals 3 cos x minus 2 cos square x. Now a slightly modified form of the previous equation is that here we have an y to the power n, where n is a real number. If n is 0, then this equation just becomes a previous equation and we can just solve using integrating factor. But now because we have this y to the power n, we have a problem. We have to remove this y from here. That is the goal. So to remove y from this side, right hand side, what we do, we divide both sides by y to the power n, and then it turns out to be y to the power minus n, here minus n plus 1 because 1y is there, and now it is qx. Now the key here is that this side, now left hand side, we have to write it as a complete differential ddx of something. To do so, we start with setting y 1 minus a is equal to z. So it gives us dz dx is 1 minus n y to the power minus a dy dx. Now I can replace this y to the power minus n dy dx over here, and as I do, I get an equation like this. This now looks like our previous form of equation that we have just solved using integrating factor. So the solution, once again, this e to the power 1 minus n px dx, that would be my integrating factor, and z is y to the power 1 minus n. So we'll come to this relation using integrating factor, and the solution follows. Let us take an example. Dy dx minus ay equals minus by square. This equation is a very famous equation, and we'll solve one problem later on in this equation. So check this solution carefully. This equation is called logistics equation, and this is used for modeling population growth. Here a and b are constants, and to solve this, I have to follow this route and divide both sides by y square. Here 1 minus n is minus 1. Then I can use this solution, and this solution will give us y to the power minus 1 e to the power ax integral b to the power x dx plus c. After the integration, this is b by a e to the power ax plus c, which gives us y equals 1 by b plus a plus c e to the power minus ax, where this constant c can be evaluated from the initial condition. To summarize, we have a recap of some of the basic ordinary differential equations. For your exercise, you solve these two equations. One is this one, is the m dx plus n dy equals 0 type equation, and the second one is probably a separable equation, looks that way. So try this and see how it works. That's all for this lecture. Thank you. I'll see you in next class.